Good morning and good afternoon, everyone. Let's talk about how to utilize LoopNest Pass. It will be presented by me, Whitney, Iterate, and your team. So we want to answer 3 questions in this tutorial: why, how, and when to write a LoopNest Pass. So let's start with the motivation. Before the LoopNest work started, if we want to write a loop optimization, there are 2 choices. Either we write a function pass or a loop pass. As an example, given a 2-level LoopNest and a pass pipeline P1, P2, if the passes are function passes, then each pass has full control of the loop processing order. Means you can go from inner to outer, outer to inner, or even reprocess them if needed. However, P1 must be completed before proceeding to P2. On the other hand, if P1 and P2 are loop passes, then loop are processed from innermost to outermost loop. And the inner loop is transformed by both passes before proceeding to the outer loop. Loop passes are implemented using Loop Pass Manager. And how it works is, first, it runs a miniature function pass pipeline to put loops into a canonical form, which is the simplified and LCSSA form right now. And then it computes function analysis required by the loop passes, for example, the dominator tree or the loop info analysis. After, it appends loops onto a work list for them to be traversed in post order, meaning from innermost to outermost. Finally, loop passes are invoked in the order of loop pipeline for each loop to be in the work list. One feature that provided by the Loop Pass Manager is loop passes can dynamically add loop back into the work list for reprocessing by other loop passes in the same pipeline. Another benefit that it provides is, since it first put the loops into their canonical form, so loop passes don't need to worry about them as they're guaranteed to be already in simplified LCSSA form. Back in 2019, there was a presentation given by Iterate, Kit, and Michael on writing loop optimization in LLVM. They described the pros and cons of the loop pass and the function pass and talk about situation when to use them. But are these our only choices, and do we have to compromise and pick one? Given an optimization that operates on a LoopNest, for example, Loop Interchange or Unroll and Jam, it makes sense to just transform the LoopNest as a unit. And a LoopNest can be uniquely identified with the outermost loop. So if the optimization is written as a loop pass, then it's have to check whether you're the outermost loop and only proceed if you're the outermost loop. If you're inner loop, then you have to explicitly skip them. You can notice that there is a lot of waste in compile time in both the Loop Pass Manager and the transformation itself. First, in the Loop Pass Manager, you're wasting time on creating the work list that we mentioned before for all the loops. And then also time wasted in invoking the transformation for all the inner loop where you're actually going to do nothing. And in the transformation itself, you are doing the check, which again is a compile time waste. And this check is just code duplication, and we know that code duplication is bad. One may suggest to use a function pass instead, because it can give you full control of the processing order. So we can directly go into the outermost loop. However, it loses the advantage provided by the Loop Pass Manager. For example, loops are no longer guaranteed to be in canonical form, meaning that either your pass will check if that's not the case and loses opportunity, or it have to put additional passes before and make sure there's no one adding other passes in between that will break the canonical form, or you will have to call helper function that do the form within your pass, which is not very great. And the other disadvantage is then you cannot loop back into the pipeline for reprocessing, which I'm not aware of another alternative of doing so if you write it as a function pass. Again, there's code duplication. So what we want is a standardized way to write optimization that operate on a LoopNest, and we don't want compile time increase, and we want to keep the benefit that Loop Pass Manager can give you. Do we have such thing? And good that, yes, we can actually implement a LoopNest pass, which is currently implement in the code base. It is implemented also using the loop path manager, so you can get all the benefit from it. You can, as it is now giving you a scope that is a LoopNest scope, so you have full control of the loop processing order within LoopNest. And finally, it gives you a standardized way to write a LoopNest optimization. Now we have the infrastructure, how to write a LoopNest path. Here's where our Google Summer Code project came in. We are a team of 5 people, where Ettore and I are the mentor, Toshiki is the student, and we have 2 volunteers, Yueting and Charles. Before getting to the demo of showing you exactly how to write a LoopNest path, let's go through some concept of perfect LoopNest and some LoopNest API relate to it. A parent-child loop pair is perfectly nested if there is no intervening user code between them. On the right-hand side, you can see a control flow graph of the simplest form of a parent-child perfectly loop pairs. And for the exact implementation that's currently in LLVM, we first check that both loops are in simplified and rotated form. In between the outer header and the inner header, it doesn't necessarily to be a direct edge. Empty blocks is also allowed to flow through. And between the inner latch and the outer latch, again, empty blocks are allowed. And on top of that, LCSSA file are also allowed. Thirdly, inner loop must be the only child of the outer loop. And finally, the outer header and outer latch blocks can only contain instruction that's either final, branch instruction, or instruction that are safe to execute speculatively. If it happened to be a binary operator, then it must be the outer loop step instruction. And the only compare instruction allowed is the inner loop guard compare and the outer loop latch compare. With this definition in mind, here you can see an example of a loop nest with loop I, J, K, L, where between I and J, they are perfectly nested, just there's nothing in between. J and K is not perfect because there's a call to full, and K and L are perfect. So with a parent-child loop pair, you can invoke the API get intervening instruction. It will give you a set of instructions that makes it imperfect. In this case, it will give you a vector with 1 instruction to the call to full. You can also ask the LoopNest object to give you the perfect loops. In this case, we have 2 elements. You notice that loop J and loop K are not in the same element because they are not perfect to each other. And finally, you can ask, get the maximum perfect depth of a loop nest, which is the number of elements in the set that the root node belongs to. So in this case, will be 2. If you're interested to know more of the LoopNest API, you can visit the link below. And here we get to the interesting demo, where Ettore will be showing you transformation to perform a simpler version of loop interchange on perfect LoopNest. He'll be showing you in 3 steps.
Today we're going to show you how to write a LoopNest transformation from scratch. What I did is to simply download the pull request that, or the branch actually, that Whitney has put together. This is the first part of the demo, so that would be LLVM 2021_tutorial_step 1. We're going to start from the header file. The first thing that we have to do is to create the class for the transformation itself. So it's called a LoopNest tutorial pass. We have a class that is derived from a pass info mixin, and this is the same as you would do for a loop pass. The difference is in the signature of the run method, and you'll notice that the first argument passed to the run method is a LoopNest object as opposed to a loop object. If this was a loop pass, it would be a loop object. But we still have available the loop analysis manager and the loop standard analysis results AR, which contains the results of the analysis that are packaged together and useful for most loop transformations. Moving on to the implementation file, we have a class called LoopNest Tutorial. This will be the class that will contain the main implementation for our transformation. Right now it's empty. We just have a run method with some traces information, just to verify that when we run the pass, we are actually entering the run method correctly, calling it correctly. We also have a static verify method, which will be used to verify that the modification done by the transformation are correct, so that all the analysis used and modified by the transformation are still up to date after the transformation runs, and also that the code, the IR code generated by the transformation itself is correct. And finally, the run method for the transformation itself. As I said before, we receive a LoopNest object, but I want to contrast here what you would have to do if you decide to write this transformation as a function pass as opposed to a LoopNest pass. So if it was a function pass, you would have to add some code to retrieve the analysis that your transformation need to use, such as the dominator tree, the loop info, and maybe a scalar evolution. And furthermore, for each loop in your function, you would have to go through each one of them and then call a method to simplify the loop, put it in canonical form, and then build a LoopNest object to then pass it to your own implementation class. This is no longer necessary. It's code that you will save. You don't have to write if you decide to use a LoopNest pass as opposed to a function pass, because the LoopNest that we receive is guaranteed to already contain loops that are in canonical form. So that's not something that you have to worry about. And also we have available the standard analysis, loop analysis. Oh, sorry, not loop analysis, the analysis that loop transformation normally use, so the dominator tree, loop info, scalar evolution, they are all contained in the loop standard analysis result. One more thing I want to show you is how to add the pass to the pass pipeline. So if you have an optimization pipeline and we want to add our new transformation, we can simply add it to a loop pass manager like we would do for any other loop pass. And this is convenient. It also means that we don't have to recompute the analysis because supposedly our pass will keep them up to date, and therefore every subsequent loop transformation pass or LoopNest transformation pass would be able to run without having to incur into the cost of recomputing the result of the standard function analysis. Finally, we have a lead test case, LoopNest.ll. This test contains a loop nest with depth 2 as two loops, the outer loop and the inner loop. And when we run it, we simply check that we receive a loop nest correctly. The loop nest indicates that the nest is perfect. It has a depth of 2, and these are the loops that are contained into that. So let's run this and see what happened. We can run it two ways. We can, of course, run the lead test using the LLVM lead tool, and it will just tell us that it passes. And we can also manually run it with these options and observe the output. And we see that, indeed, we receive the expected information from the pass itself. And this concludes the first part of the demo. First part, we have created the framework, or basically the skeleton, for our LoopNest pass. In this part, we're going to show you how to use the API, the most useful API in the LoopNest class, to filter out loops that your transformation should be transforming versus one that he has to skip. So again, I want to give credit to Whitney. Whitney had created like all these demos, and these are up on her public GitHub. So what we're going to do, we're just going to go through the second pull request, and if you want to know what changed this pull request, it'll show you over there. So looking at the implementation of the main class for the transformation, LoopNest tutorial, we have added in this step some filtering. So we have a check we're checking if our loop nest is a candidate for our transformation. If it is not a candidate, we're going to skip it, and otherwise we're going to process this further. So this is implemented using this private member function, isCandidate. It will receive a loop nest, and it will uses a lot of the APIs that are in the LoopNest object itself, in the LoopNest class. For example, I already mentioned before that the loop nest received by a LoopNest transformation pass are guaranteed to all be in simplified form. And so we can simply assert that indeed they are all in simplified form or something went wrong. We also would like to have our loops in rotated form. So there is another API in the LoopNest object to check whether all loops contained in the LoopNest are in rotated forms. And if they're not, or even if one of them is not, this is not a candidate for our transformation. We can check that the exit block of the outermost loop exist. If it doesn't exist, we're going to skip our transformation, and so on. So, for example, in this case, we artificially limit the transformation to operate on loop nests that have only 2 loops. That's an artificial limitation, but just to show you that there is this kind of API that may be useful in some instances. And also, we're checking that the loop nest is entirely perfect, so that there are no loop nests or subloops or subloop nests that are not perfect within the loop nest. And if all these conditions are okay, then we have found a candidate for our transformation, and we can process it further. So now I'm going to run the lead test. The lead test basically is the same as in the first pass, except that we're going to verify that the loop nest, which is rooted by the outermost loop call header.outer somewhat arbitrarily, is a candidate for interchange. And it is because we satisfy all the preconditions that we have encoded in the isCandidate member function. This is the third and final part of the demo. In the previous part, we showed you how to write the skeleton for a loop nest transformation pass. And in this part, we're going to fill in the remaining pieces, so implement the actual transformation to do the loop interchange. As you remember, in the second part of the demo, we discussed how we can write a member function called isCandidate to filter out loop nests that do not abide to certain conditions, or loop nests that were not prepared to handle. So, for example, if a loop nest is not in rotated form or has more than 2 loops, we're going to throw it away and return false over here. And so what's remaining are only loop nests that are candidates for the interchange. And so we are responsible to implement the interchange code, which is done in this loop interchange method. So let's go take a look at that. Here it is, loop interchange. So what do we have to do to interchange the 2 loop in a perfect loop nest? So it's very simple. All we have to do is to go into the loop preheader, or let's say the preheader of the entire nest, or the preheader of the outer loop, which now branches to the header of the outermost loop, and make that branch flow into the header of what's now the innermost loop. And then we have to fix up the branch into the header of the innermost loop and make it flow or branch into the header of what's now the outer loop. And the branch inside the header of the outer loop will have to go into, flow into the body of the loop, so that the two loops are interchanged if we do that. So this is what this function is going to do. The first thing that it does is to create some basic blocks, or split some basic blocks, and then it's going to go into adjust the loop branches, which does exactly what I just told right now. I just said that now. So we collect some information about what's the outer preheader, the outer latch, and so on. We print it out, and then we start to call this lambda function, which is defined over here, update successors. So what's interesting about this lambda function, beside the fact that it will set, you know, the new successor of a branch instruction, what's interesting that as we do that, so as we modify the LLVM IR that we're going to be producing, or as we generate the LLVM IR that we are producing, we are also collecting updates to the dominator tree. Because if we inject new blocks and we change the basically the control flow, the dominance relationship in this LoopNest will no longer, it changes, no longer up to date. So we are responsible as a loop transformation pass to keep the information in the dominator tree data structure up to date. So the way that this is done the same way for a loop transformation pass as it is done for a loop pass. We cache or we collect these changes into the DT updates object. And then at the end of this function, we can simply apply them all to the dominator tree object itself. And this line of code will make the dominator tree become up to date with respect to the new IR that we are generating. After that's done, we finish the job by calling restructure loops, which is a small function at the end. So, you know, we need to also update the loop info to indicate that now we have a new top level loop in the loop nest and similar things. We remove some blocks and we're done. So let's take a look at the test case. So the test case is the same as before, except that now we have finished implementing all the proper checks or lead checks to verify that the transformation works as it should. And so let's run this test case. Here it is. And actually we can just run the pass itself and then look at the output. As before, we have a loop nest. We are entering all in the run method of our transformation pass, which is going to call all the code that we have brought. So the first part is splitting the blocks. We can take a look at the new blocks. We're adjusting the loop branches. And then finally, the final code that we produce is this. And we can see just by inspection that the pre-header of the entire loop nest, which was, let me show it over here, which actually branching to the header of the outer loop, is now branching to the header of the inner loop. And the header of the inner loop is branching to the header of the outer loop. The header of the outer loop is now branching to the body of the loop. So it looks like the interchange was done correctly, and that's about it. So this check will check exactly what that point. So thanks for watching, and I hope that you learned something today about how to use a LoopNest transformation pass. Okay, so like I said before, I hope that you guys enjoyed the video. I certainly enjoyed shooting it. And now I'm going to introduce Ting, which is going to go through how to write a LoopNest pass and his experience with the Google Summer of Code project and program. You're muted.
Sorry. Well, here are the scenarios that we found that were useful for a LoopNest pass, and I'm going to go through them one by one. The first is that when a LoopNest pass, it runs on a LoopNest as a unit of code. Well, currently, before LoopNest pass, when you want to operate on multiple loops, then you would use a function pass. Well, it is to be more intuitive for a loop transformation pass to be used as a LoopNest pass, right? And the next thing is that being a LoopNest pass allows the pass to be in the loop pass pipeline, and this would allow the pass to use utilities provided by the pipeline. And for an example, you can see that here is the flattening as a function pass. And inside the main function of the run function of the pass, you can see that it has to call function analysis manager to get the wider scope analysis structures. Well, being a LoopNest pass means that the loop pass pipeline already provides the structure, and so these lines of codes are needed. And then for a function pass, the function pass pipeline doesn't guarantee the loops to be simplified in LCSSA form. So before the optimization happens, the pass itself has to do pre-process to the loops. And for a LoopNest pass, the loop pass pipeline already guarantees that the loops are in the simplified and LCSSA form. So the pre-process of the optimizations are needed, and these lines can be deleted. And so overall, you can see that a loop flattened pass as a LoopNest pass would allow the author to focus on the pass itself and don't need to write boilerplates for the optimization pass. The second scenario is that when you want to control the whole LoopNest to do some code gens. Well, think of LoopATM recognize. It is a optimization that recognizes certain bounded skivs. And right now you're trying to do a aggressive optimization that you're trying to add runtime checks to the skiv to make it bounded. Well, first you would want to think that in a loop pass, we would add runtime checks loop by loop. Well, that would lead to the number of versions grow exponentially, as you can see on the slide. Well, then if we can have a more reasonable trade-off, like we can collect all runtime checks and then only have a versioning at the outside of the outermost loop. This allows us to do an aggressive optimization while avoiding the problem of code bloat. And LoopNest Pass is suitable for this situation. Well, first of all, LoopNest Pass provides API for us to get the outermost loop, and it already collects the loops, so we can iterate through the loops, collect runtime checks we needed, and add them to the whole LoopNest. The third scenario we thought of was that LoopNest Pass can be used to preserve perfectly nested loops. Well, why do we need them? Some passes can benefit or be simplified when dealing with perfectly nested loops. For example, loop interchange. And for passes like this, if we want to maximize the effectiveness, then we want to preserve the property as much as possible. And why do we want to use a LoopNest pass? Because a LoopNest pass captures the whole LoopNest, which is a wider scope, and it allows us to check for the property and to help preserve it. Take loop invariant code motion as an example. Here's, as you can see on the slide, after LICM, you can see that variable X can only be hoisted out of loop J, and this breaks the perfectly nested loop property. Well, if we create another pass, a LoopNest invariant code motion, then before hoisting any instructions, we can check that if it can be hoisted out of the outermost loop and only hoist the instructions that can be hoisted out of the whole LoopNest. And so LNICM wouldn't break the property perfectly nested loop. However, we can't just directly replace LICM with LNICM. Well, here's an example why. Assuming that there are two passes in the loop pipeline, first LICM, then pass X. When dealing with a nested loop, the loop pipeline would iterate first from innermost to outermost. And in the following sequence, it would first do LICM inner loop, then pass X inner loop, LICM outer loop, then pass X outer loop. Well, now if we want to replace LICM with LNICM, then before pass X inner loop, the pass pipeline would do nothing. This would be a potential hazard because if pass X is a pass that relies on the result of LICM inner loop, then the results may not be correct right here. So we thought of a potential way of solving this. Maybe we can collect passes that want to preserve perfectly nested loops or to utilize them and create a whole new pipeline for them. Well, possibilities are not yet explored and discussions are welcomed. So I've introduced 3 scenarios that we found a good fit for a LoopNest pass in this year's GSOC project. First is a LoopNest pass can operate a LoopNest as a unit of code. Second, a LoopNest pass controls the whole LoopNest and helps code generation. And third one is a LoopNest pass can help us preserve perfectly nested loop property. And so that's the end of the presentation. I want to thank everyone for the contribution and the reviewers and commentators, and also the mentors of this project. And now loop optimizations don't limit to only function pass or loop passes. So let's start using LoopNest passes. And that's the end of this presentation. Bardia, do we have any questions?
Okay, thank you, presenters, and thanks to the audience for attending this session. At this point, you can paste your questions into the Q&A box at the bottom of the page. Currently, I don't see any questions, but I do have one. I just wanted to ask, what are some of the limitations of the existing implementation of the LoopNest pass, and how can we go about improving it?
So one example is one reason people don't want to use a loop pass before is you have to preserve all the analysis. Means you have to have a lot of code kind of unrelated to your actual transformation to update all the analysis, which we kind of have to do that if we want to have a more efficient loop pass manager for other passes to use it without recomputing it. But we are thinking that it could be useful for author to have an option to say optionally they can rely on the loop pass manager to update the analysis instead of they forced to do it.
Okay. I'm not seeing any questions posted yet. So maybe I can ask another question. I think the loop pass doesn't allow a transformation to change the function. I would assume that this limitation is also inherited by the LoopNest pass as well.
I don't think loop pass cannot change the function. I do see some existing loop pass that kind of change it, and I don't think it's a strict requirement.
Okay.
Yeah, it's not a strict requirement, but it's in theory a LoopNest pass should limit itself to change things inside the loop. So same thing would apply to a LoopNest pass. They are allowed to change code outside of the LoopNest, but we do recommend that people limit themselves to the actual LoopNest itself, right? So the advantage of a LoopNest pass is that the loop, if you were to be the innermost loop and you want to change a loop that is your parent or your grandparent, then you can do that. You shouldn't do that with a LoopNest pass. You have the visibility for the entire LoopNest, and so you are free to change anything inside the loop, but you should not change anything inside the function.
Makes sense. Thank you. I still don't see questions.
Maybe I can use this opportunity, it's not a question, but we have time to advertise about the idea of non-student joining a Google Summer of Code project, even if they don't think they're expert on the area, like your team that volunteer to help out in this Google Summer of Code, then he can learn more of LLVM code base and about topic that he's interested, even if he's not a student. Do you want to say something about it, your team?
Yeah, I had fun like this Google Summer of Code participating in the project, and it helped me to get to know the community and to actually send patches and know what's going on inside LLVM. Yeah. And I also want to thank the mentors. They really helped out during my patches.
Okay, great. Thanks again for the insightful talk, and thanks for your participation. At this point, I do not see any more questions, so I think that concludes this talk. Thank you.